SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will start a series of lectures based on external flows. And in external flows, first we will cover flow and heat transfer over a heated flat surface. Here we can see heated flat surfaces on which fluid is flowing, and depending on the situation, whether Prandtl number less than 1 or Prandtl number greater than 1, the analysis will take up proper form. However, in this discussion, we will solve the velocity boundary layer equation and the thermal boundary layer equation to find the heat transfer coefficient on a heated flat plate over which a fluid stream, in this case we'll consider, obviously since plate is heated, the fluid stream is cooler, and heat transfer will take place from the plate to the flowing fluid. Now we will first discuss the solution of velocity boundary layer, and solution of velocity boundary layer is basically known as Blasius solution. This is the simplest example of boundary layer flow over a flat plate. As we can see, outside the boundary layer it is potential flow, and through the boundary layer velocity is approaching from 0 to finally the free stream velocity. And in the potential flow region, there is no velocity gradient. Velocity gradient is present only within the boundary layer. And the governing equations are, we have seen already, we derived earlier, boundary layer equation, u del u del x plus v del u del y equal to nu del 2u del y2, and continuity equation del u del x plus del v del y equal to 0. Now if we rewrite the boundary layer equation at the edge of boundary layer, we'll be able to write u del u del x equal to minus 1 by rho del p del x. And then at the edge of the boundary layer, if we substitute the velocity as u infinity, the velocity in x direction, u infinity du infinity dx equal to minus 1 by rho dp dx. Since u infinity, that is free stream velocity for flow over a flat plate, doesn't have any gradient, so dp dx is basically 0. So we have written down formally the boundary conditions at y equal to 0, u equal to 0, no slip condition, v equal to 0, impervious condition, and at y equal to infinity, u equal to u infinity. Substitution of minus 1 by rho del p del x in the boundary layer momentum equation in terms of free stream velocity, which we were talking about, u infinity du infinity dx, which is equal to 0. Hence, the governing equation doesn't contain any pressure gradient term. The characteristics parameters of this problem are u, u infinity, nu, x and y. Before we proceed further, we will discuss little about the laws of similarity, because Blasius solution is also called similarity solution, and we will solve this problem with respect to two similarity variables. Now, u component of velocity has the property that two profiles, u profile at two different x location, they look alike but they differ by a scale factor. So velocity profiles uxy at all values of ax can be made same if they are plotted in coordinates which have been made dimensionless with reference to the scale factors. The local free stream velocity ux we have written, which is in general for flat plate u infinity, but if it is a surface with different shape, that means surface has a curvature, then the free stream will not be u infinity at every x. It will be a function of x, but it will be unaffected by viscosity. So the free stream, more general terminology, free stream can be expressed as uppercase u as a function of x. And because the dimensionless ux varies with y between 0 and unity at all locations, scale factor for y can be called as g, and this is proportional to local boundary layer thickness, so that y itself varies between 0 and unity. So we can write u as function of x1 at a location x1, y divided by gx1 divided by the free stream velocity u at x1 location, equal to again velocity at another location, say x2, where the boundary layer thickness is gx2. So y by gx2 divided by free stream velocity at that location. So this can be expressed in this way. And also we can observe that in this problem we have the variables that are involved: u, u infinity, nu, x, y. Basically 5 variables are involved, and it is reducible for a dimensional relation, because here the length and time, these are the two units involved in all these variables we have used. So 5 minus 2, we are supposed to get 3 dimensionless quantities, 3 non-dimensional parameters. But for boundary layer and the boundary layer equations, a spatial similarity variable is available, and then only 2 such spatial similarity variables are available, and only 2 such quantities are needed. When it is possible, the flow field will, and when it is possible when to express the flow field in this manner. It can be called a self-similar situation, or these are called similarity parameters. For self-similar flow, the x component of velocity has the property that two profiles of u at different locations differ only by a scale factor that is at best a function of x. So u profile, if we draw within the boundary layer at different x locations, they are analogous, but they differ by a scale. It is possible to write, instead of plotting u against y at different x locations, we can plot u by u infinity, that is free stream velocity. This is a similarity parameter equal to or as a function of, say, eta. And this eta is then another similarity parameter where eta is expressed as y by delta. In other words, we can write u by u infinity as f y by delta, and y by delta is proportional to root over nu x by u infinity. So for Blasius problem, the similarity law is u by u infinity equal to f y by root over nu x by u infinity. And y by root over nu x by u infinity is a parameter eta. That's what we said, that eta is y by delta or y by root over nu x by u infinity. So u by u infinity, the way it will vary against eta, that is the unique variation of the boundary layer thickness. Now, or unique variation of velocity across the boundary layer. So eta equal to y by delta, delta is proportional to nu x by u infinity, or eta is y divided by root over nu x by u infinity. Now let us define stream function, and then from our basic definition, stream function is integral u dy. Now u, if we express in terms of u infinity, then because we have seen u by u infinity is f eta, so u we can write as u infinity into f eta, u infinity into f eta into root over nu x by u infinity d eta. That is, u we have written this way, so dy we are writing as d eta. So since y is eta is y by root over nu x by u infinity, dy equal to d eta into root over nu x by u infinity. So we have written then u and dy in terms of u infinity and d eta, and this is simple algebra. It is root over u infinity nu x into integral uppercase f eta d eta. Now uppercase f eta d eta, after having integrated, we can write that lowercase f eta. So psi equal to root over u infinity nu x f eta plus cx integration constant, where f eta, f lowercase, equal to integral f eta d eta, this f is uppercase f, and cx equal to 0 if the free stream function at the solid surface is set equal to 0. We know that if the stream function at the solid surface, stream function is also representative of the mass flow rate or the volume flow rate. So psi, if we rewrite psi on the solid surface, stream function at the solid surface is value of stream function is 0. So Cx becomes 0. If Cx becomes 0, we can write psi equal to root over nu x into u infinity f eta. Root over nu x into u infinity f eta, Cx equal to 0. And eta is as usual y by root over nu x by u infinity. So from here, when we know psi, we can write or we can find out u. U is del psi del y, which is del psi del eta into del eta del y, and we can write from these two then u infinity f prime eta. Similarly, v we know when psi is function of eta and x, v can be written as minus del psi del x plus del psi del eta into del eta del x. We know psi, we know eta. From here we find out del psi del x, del psi del eta into del eta del x. And then v finally produces half root over nu x by u infinity multiplied by within bracket square bracket eta f prime eta minus f eta. So basically we are now trying to express the boundary layer equation in terms of psi and eta variables. So in boundary layer equation we have u del x plus v del u del y equal to nu del 2u del y2. U and v we have found out. Now del u del x, again this is basically del u del y into del y del x. If we substitute term by term, we will get minus u infinity by 2 eta by x f double prime eta. Del u del y we can straightforward write from here u infinity root over that means u infinity into f double prime eta, then del eta del y. So basically u infinity into root over u infinity by nu x into f double prime eta. Del 2 u del y2 we differentiate again del u del y, and then we will, that means we differentiate this quantity with respect to eta, and then again del eta del y. So we will get u infinity square by nu x into f triple prime eta. So we have evaluated all the terms involved in boundary layer equation in term by term with respect to psi and eta variables. And then if we substitute, because we have found out u, v, del u del x, del u del y, del 2u del y2, so the governing equation u del u del x plus v del u del y equal to nu del 2u del y2, all the terms are available. If we substitute and do some algebraic operation, we will get 2f triple prime eta plus f eta into f double prime eta. So 2f triple prime eta plus f into f double prime eta equal to 0. 2f triple prime eta plus f eta into f double prime eta equal to 0. And boundary conditions, if we try to recapitulate, at y equal to 0, u equal to 0, no slip condition, v equal to 0, impervious boundary condition. And if we write this or substitute this here, if we want to get v equal to 0, u equal to 0, for the value y equal to 0, that means for the corresponding value of eta equal to 0, we will get at eta equal to 0. This is just to be brief. Some places at I have written at the rate with at the rate symbol, but it means at eta equal to 0, f prime eta equal to 0. This is simply from here at eta equal to 0, u has to be 0. That means u infinity cannot be 0, f prime eta is 0. So at eta equal to 0, f prime eta is 0. And then again at eta equal to 0, if we write v equal to 0, we'll see that at eta equal to 0, f is 0, f eta is 0. Similarly, at y equal to infinity, u equal to u infinity. So here we can go back again. At y equal to infinity, u equal to u infinity. That means at y equal to infinity, f prime eta is 0, or f prime infinity, u equal to u infinity at eta equal to infinity. So f prime eta at eta equal to infinity will be 1. This u is u infinity, this is u infinity, so f prime value will be 1. So at u equal to infinity, u equal to u infinity, which will produce at eta equal to infinity, f prime eta is 1. We have shown that. Now, this equation, governing equation, is a third order nonlinear equation. And it was a formidable job when Blasius did this work to find analytical solution of this equation. And what Blasius did, he attempted a series solution. Series solution means it's a power series in eta. That means for the small values of eta. So we have written also, Blasius obtained this solution in the form of a series expanded around eta equal to 0. Let us assume a power series. This power series is for small values of eta. So we have taken the power series as a naught plus a1 eta plus a2 by factorial 2 eta square plus a3 by factorial 3 eta cube plus a4 by factorial 4 eta 4, and higher order terms, but this is a convergent series. Now f prime, we have simply found out the derivative of that series, f prime eta equal to, then a1, a naught is knocked out, a1 plus a2 eta plus a3 by factorial 2 eta square plus a4 by factorial 3 eta cube. We can differentiate it again for finding f double prime eta, and we get a2 plus a3 eta plus a4 by factorial 2 eta square plus a5 by factorial 3 eta cube, and so on. And finally f triple prime eta. So very clearly we can see a3 plus a4 eta plus a5 by factorial 2 eta square, and so on. Now here itself we can see that if we apply these two boundary conditions, that is at eta equal to 0, f eta equal to 0, we will get a0 equal to 0. And at eta equal to 0, f prime eta equal to 0, we will get a1 equal to 0. Simply from here, by looking at this, we can identify that, we can find out that. So now we will substitute the boundary conditions to basically find out the constants. So I have already mentioned about it. Eta equal to 0, f prime is 0, and eta equal to 0, f is 0. Now from these two, a naught equal to 0, eta equal to 0, f is 0, a naught 0, and eta equal to 0, f prime eta equal to 0, a1 will be 0, a1 is 0. Then we can apply a third boundary condition, which is a derived boundary condition. If we look at the boundary layer equation, u del u del x plus v del u del y equal to nu del 2u del y2 equal to nu del 2u del y2. Now at y equal to 0, if we in this equation write u equal to 0, v equal to 0, then basically the left hand side becomes 0. Left hand side we have u del u del x plus v del u del y. Right hand side we have nu del 2u del y2. So left hand side, since u is 0, v is 0, left hand side is 0. And right hand side we are left with nu del 2u del y2. Nu cannot be 0. So del 2u del y2 is 0 at y equal to 0. And del 2u del y2 is basically f triple prime, if we write it in terms of eta variable. So that means at y equal to 0, del 2u del y2 0, which leads to at eta equal to 0, f triple prime eta equal to 0. Now if we then use in this where we have written f prime, f double prime, f triple prime. So if at eta equal to 0, f triple prime eta is 0, that means obviously a3 is 0. So we have written a3 is 0. So now having found a0 equal to 0, a1 equal to 0, a3 equal to 0, in the expression for f, f prime, f double prime and f triple prime, we implement that. And then after substituting a0 equal to 0, a1 equal to 0, a3 equal to 0, if we substitute f triple prime here, f here and f double prime here from these expressions. So we get 2f triple prime plus f into f double prime equal to 0. Exactly, that's what we have to do. 2f triple prime eta plus f eta into f double prime eta equal to, we have to set that equal to 0. Now if really this is equal to 0, then all the coefficients related to any power of eta should be 0. So coefficient of different powers of eta we collect and then equate those coefficients equal to 0. If we do that, for example, first a coefficient of only eta from the after multiplication, that is twice a4, a4 equal to 0. Then eta square, after multiplication, if we collect coefficients of eta square, twice a5 by factorial 2 plus a2 square by factorial 2 equal to 0. Then eta cube, all the coefficients associated with eta cube, if we set them equal to 0, we will be able to write 2a6 by factorial 3 equal to 0. In the similar way, we will be able to find twice a7 by factorial 4 plus a2a4 by factorial 4 plus a2a4 by factorial 2 into factorial 2. We'll get twice a8 by factorial 5 plus a2a5 by factorial 5 plus a2 a5 divided by factorial 2 into factorial 3 equal to 0. So this, now if we really try to clean it up, we will see that a4 equal to a6 equal to a7, all these terms are 0. And a5 is or can be expressed as minus a2 square by 2. A8 is 11 by 4 a2 cube. A11 is minus 375 by 8 a2 power 4. So we can now, having found out all the constants in terms of a2, we can reformulate the series as f eta equal to a2 by factorial 2 into eta square minus half a2 square by factorial 5 into eta 5 plus 11 by 4 a2 cube by factorial 8 into eta power 8 minus 1 by 8 375 by factorial 11 into a2 power 4 eta power 11. And we can rearrange that again as f eta equal to a2 power 1/3 into, again, expression of a series, that is a2 power 1/3 eta square by factorial 2 minus half a2 power 1/3 eta to the power 5 by factorial 5 plus 11 by 4. Again, now variable is becoming a2 power 1/3 into eta. So a2 power 1/3 into eta whole to the power 8 factorial 8 minus 1 by 8 375 a2 power 1/3 into eta whole to the power 11 by factorial 11. So we can write this as f eta equal to a2 power 1/3 into uppercase f, another series, a2 power 1/3 into eta. Now this equation satisfies this series in a2 power 1/3 eta into a2 power 1/3. This has, we have seen, already satisfied all the boundary conditions at eta equal to 0. That means at eta equal to 0, it has satisfied u equal to 0, v equal to 0, they are equivalent. It has satisfied at eta equal to 0, what I was saying, u equal to 0, v equal to 0, del 2u, del y2 equal to 0. But it has not yet satisfied the boundary condition at y equal to infinity or eta equal to infinity. So for that, what we have to do, because at y equal to infinity or eta equal to infinity, it is f prime eta equal to 1. So under the limiting condition, we are saying that a2 power 2/3, after finding out derivation of f eta, we have to find out f prime eta. So a2 power 2/3 f prime a2 power 1/3 eta, as eta tends to infinity, that means now this is equivalent to f prime infinity equal to 1. We know at y equal to infinity, u by u infinity equal to 1, because at y equal to infinity or eta equal to infinity, u becomes equal to u infinity. Lowercase u outside the boundary layer. It has reached the boundary layer interface, and when it goes to outside the boundary layer, it is u infinity. So u by u infinity equal to 1 just at the edge of boundary layer. And from here we can see that a2 is 1 by f prime eta. Eta tends to infinity, and obviously then if we write it from here, this is equal to 1. So a2 is 1 by f prime eta to the power 1/3, and this has to be evaluated numerically, taking the full series. So the value of a2 can be determined numerically to a good degree of accuracy. This was done by Howard, and he found a2 as 0.33206. So a2 from this solution, series solution, of course, finally a2 was evaluated numerically. Up to that point, everything was done analytically, and a2 was found as 0.33206. Now what we did here, that can be done through a full numerical approach. And then what we do, we write f triple prime twice f triple prime eta plus f eta into f double prime eta equal to 0. This third order nonlinear equation can be expressed as a combination of three first order equations, where f prime is g, g prime is h, and h prime is half f into h. So f prime is g, g prime means f double prime, and h prime means f triple prime. So f triple prime is equal to minus half f into f double prime, minus half f into h, because h is g prime is f double prime. So this is a way we can write or rewrite Blasius equation. Then what we do, we solve these three equations simultaneously the way we solve the first order differential equations. Now here that means f prime equal to g. So that is, for solving this, we will need basically the initial condition f naught. Now the condition if naught, which is the initial condition for eta equal to 0, we know. We have already seen that since eta equal to 0, u equal to 0 and v equal to 0, f prime not equal to 0 and f not equal to 0. So f naught is known for solving this. Now this equation means f double prime equal to some quantity, some expression. Now for this, any equation f double prime equal to some known right hand side, we can solve basically if we write it in this way, first order equation g prime, so we can write, for example, dg dx equal to some expression. Now that we can solve if we know the value of g naught. Value of g naught means g means f prime, so value of f prime naught, so that is also known. So initial condition for this is known, initial condition for this is known, but this is basically g prime, so h prime, so we have to know h0. Now h0 means f double prime at but we do not have that condition here, right? See, for h prime equal to some expression, for solving this we have to know h0 at eta equal to 0, but we do not have any condition for h0. But we have another condition, which is at eta equal to infinity, f prime equal to 1. That means g infinity equal to 1. F prime eta equal to 1, which means g infinity equal to 1. Now that means, as I said, that this is equation in f prime, we need f0, we have equation in g prime, we need g0 or f prime 0, we have. This is equation in h prime, we need a condition at h naught, we don't have, but we have additional condition which is basically at g infinity, f prime equal to, at eta equal to infinity, f prime is 1. That means f prime is 1 at eta equal to infinity, and at eta equal to infinity g is then known, g is 1, g infinity 1. So note that the equations for f and g have initial values. The value of h naught is not known. This is not an usual initial value problem. We handle the problem as an initial value problem by choosing the value of h naught. For h prime equal to an expression, for solving this we have to have a value of h naught, initial value, but we don't have it here. So we do it by choosing a value of h naught, and then, as I said, that we can solve for f eta, g eta and h eta. But since we have chosen this value, we can choose then any value and get a solution. It's not like that. The value that we choose to solve this equation, that means H naught, this should lead to a situation so that G infinity has to be 1, because at eta equal to infinity, f prime is 1. So G infinity, f prime infinity is 1, that is known. G infinity is 1, that is known. So in general, G infinity equal to 1 will not be satisfied for the function G arising from the numerical solution. We then choose other initial value of H so that we can find H0, which results in G infinity equal to 1. So basically, we try with different initial values of H and observe for which value G infinity is 1. And this method is called shooting technique. And this shooting technique is implemented through the numerical integration following Runge-Kutta method. That means, as I said, that if we know F naught, we can find out F eta. If we know G naught, we can find out G as a function of eta. That means F prime as a function of eta. So we can find out F, G, H, all three quantities, and finally we have to check whether G infinity equal to 1. And in eta direction, we go step by step. For small increments of eta, we use Runge-Kutta method, and this Runge-Kutta method is interrelated because we calculate F, we calculate G, we calculate H, and F and G are linked to H calculation, F is linked to G calculation, and so on. So, and we do this, we go from Fn initial value to Fn plus 1. That means a small increment in eta direction. And this is given, Fn plus 1 is given by Fn plus 1/6 K1 plus twice K2 plus twice K3 plus K4, usual Runge-Kutta method. Gn plus 1 equal to Gn plus 1/6 L1 plus twice L2 plus twice L3 plus L4. Hn plus 1 equal to Hn plus 1/6 M1 plus twice M2 plus twice M3 plus M4. So if one moves from eta n to eta n plus 1 and through a small increment, that means eta n plus h, h is the interval, maybe 0.01, some such interval, then the values of k, l and m will be known, and then we can find out basically df d eta, dg d eta, dh d eta. And k1, l1, m1, these are basically h is the increment small lowercase h, h into f1 the function at fn, gn, hn, eta n, h into f2 fn, gn, hn, eta n, h interval into f3 fn, gn, hn, eta n. Similarly, K2, we can find out h, the interval, into the function where fn plus fn is incremented by fn plus k1 by 2, gn is gn plus l1 by 2, hn is hn plus m1 by 2, and eta as eta plus h by 2. So L2 we find out this way, M2 we find out this way. So these are the quantities as we have seen: K1, L1, M1, then K2, L2, M2, K3, L3, M3, K4, L4, M4. So we have to find out this, and then we have seen this here. Our functions f1, f2 and f3 are g, h and minus f h by 2. Then at a distance delta eta from the wall, we have f delta eta equal to initial value of f plus df d eta into delta eta. Df d eta means at 0 into delta eta. So that means df d eta means g. So g0 into delta eta. Similarly, d delta eta equal to g at 0 plus h0 into delta eta. So h delta eta equal to h0 plus h prime 0 delta eta. So this way our solution we can perform the Runge-Kutta integration. As it has been mentioned, f double prime 0 equal to h0 is unknown. h0 equal to say any guess value s must be determined such that the condition f prime infinity, that means g infinity equal to 1, is satisfied. The condition at infinity is usually approximated at a finite value of eta. Now here eta equal to 10 is a very large value. So if we can perform the integration up to eta equal to 10 and then plot f, g and h, will be sure that whether solution has reached, and check is if g infinity is 1. Asymptotically it will reach 1 and continue. Now value of h naught now can be calculated finding h tilde naught at which g infinity crosses unity. So this is basically in the solution. See, for example, for some initial value of h naught, we have got this value. G infinity is varying this way. It is basically asymptotically reaching a value, some value. We have not given exact quantity here, maybe 0.6, 0.5, something like that. Then another guess, we can see variation of g, and it has crossed also 1. So now from these two, we can see that we can find out exact initial value for which g will reach 1. And that can be done. I'll come back to this expression just after a second. We'll show it here again. So for initial guess h naught, this is the variation. Second guess h naught 1, second guess h naught 2, this is the variation. So h naught 1, g infinity is this. H naught 2, g infinity 2 is this. But we want g infinity value as 1. So if g infinity has to be 1, then from this similar triangle, we can find out a better guess. And we can see whether for that better guess, g infinity is becoming 1. If that doesn't become, it again overshoots, then we can find out, just repeat the same method, a better guess between h tilde naught and h naught 1. Between these two, we can find out a better guess. So each time g infinity versus eta, for proper g infinity, that means G infinity equal to 1 has to be checked. And in this similar triangle, we have mentioned it earlier, we just write H tilde naught minus H naught 1 divided by 1 by G infinity 1 equal to H naught 2 minus H naught 1 divided by G infinity 2 minus G infinity 1. From this similar triangle, we can write, and H naught tilde is not known and H naught tilde can be found out. Again, we can apply the same method to find out a better guess between these two values. Final object is to get a value for which we will get G infinity equal to 1 for eta, large value of eta. And we can show the final solution. All of you probably have listened to this name, yet another big name like Blasius, Hermann Schlichting. Schlichting has a very good book on boundary layer theory, and this table is has been taken from Schlichting's book. So this is basically, you can see eta, we started with 0 and small increment. I mean, increments are even smaller, actually 0.01, but we have just given some, we cannot give such a huge table. We have just given, some intermediate values to show how f varies, how f prime, that is G, varies, and how f double prime, that is H, varies. And we can see that this value of H naught, which has worked well, is 0.33206. Amazing similarity with Howard's solution. So with this guess value, we have seen that we get variation of f versus eta, f prime versus eta, and f double prime versus eta. And here another observation is, we can see around 5 f prime reaches 0.99. And what is f prime? U by u infinity, small u by uppercase u. So small u reaches uppercase u, that means close to uppercase u, 0.99155. So lowercase u by uppercase u is f prime. Now for f prime equal to 5, lowercase u reaches almost uppercase u, 0.9915. That means it has reached the edge of boundary layer at eta equal to 5. We'll explain even more. So after that, so that means we have got the complete solution. This was our target. This is a actually velocity profile. How the u by u infinity, that means f prime, varying from 0 to a larger value of eta through small increments. That means the entire velocity profile within the boundary layer. Having found out that, we can calculate shear stress. Shear stress is nothing but tau wall into mu del u del y at y equal to 0. So again we substitute u by u infinity, y as eta, and then we can write tau wall is mu u infinity del eta, del u del y is nothing but f prime eta into del eta del y. This should be eta. del eta del y at eta equal to 0. And f prime eta at eta equal to 0, we can see f prime del eta of f prime eta at eta equal to 0. That means f double prime eta at eta equal to 0 is 0.33206. So 0.33206, and then because we have changed the variable from y to eta, this factor will come root over nu x by u infinity. So tau wall we get 0.332 rho u infinity square divided by root over rex. Rex is u infinity into x by nu. So this is Reynolds number based on the length of the location from the leading edge of the plate. It means x. So u infinity x by nu. Local skin friction coefficient CFX, tau wall divided by just the non-dimensional value, half rho u infinity square, we can get 0.664 divided by root over rex. Total friction force per unit length is basically integration of tau wall dx between 0 and L, when L is the total plate length. Then we substitute the value of tau wall that we got here and perform the integration, and finally we get, you can do it by yourself, 0.664 rho u infinity square into root over nu L by u infinity. Similarly, average skin friction coefficient, which is given by total friction force divided by half rho u infinity square into L. This is given by 1.328 divided by root over REL. Since it is for the total plate, so this REL is u infinity into length of the plate by nu. From the table, it is also seen that f prime equal to g equal to 0.99 for eta equal to 5. I've already mentioned about it. For eta equal to 5, f prime reaches 0.99. So for eta equal to, so u by u infinity reaches 0.99 at eta equal to 5. So delta divided by root over nu x by u infinity, that means eta becomes 5 when u reaches u infinity. So that delta is given by delta by x equal to 5 by root over rex. So we can say that from exact solution we get that delta by x is 5 divided by root over rex, where rex is given by u infinity into x divided by nu. And also we can see delta varies as x to the power half. If we take x to this side, root over rex has one root x at the denominator, so delta varies as x power half. Now this is about the velocity boundary layer solution, and then we have to connect it with the thermal boundary layer solution to get the heat transfer coefficient. Here we have gotten skin friction coefficient for the velocity profile that we have obtained. Similarly, with this velocity and the temperature profile that will be determined in the next part of the solution, thermal boundary layer solution, we'll be able to predict the Nusselt number or heat transfer coefficient. Thank you very much for your interest. Thank you.